We're now going to take a look at another special type of first order differential equation that at the outset is neither linear nor separable, but again, through a clever use of a substitution, we'll be able to convert it into an equation that we know how to solve, right? And these are called Bernoulli equations. So let's go ahead and give you the general form of a Bernoulli equation, right? So a first order, let's just say dE of the form, and this is what they look like. So dy dx plus p of x times y is equal to q of x times y to the n. So this, right, is called a Bernoulli equation, right? Bernoulli equation, and Bernoulli is actually the last name of a family that is just, I mean, it's just littered with wonderful mathematicians, right? So you might come across the word Bernoulli in a probability and statistics class or in a mathematical physics class. They're all over, right? And as far as first order differential equations are concerned, ones that look like this are said to be Bernoulli, well, is a Bernoulli equation. Here we go. Got to get my grammar straight. Now, when you look at this, this is eerily similar to the general form or the standard form of a linear first order dE, correct? Like if the y to the n factor wasn't there, right, then yeah, it would be linear and we could use our integrating factor method. Now, what is n? N technically can be any real number, right? The thing though is if n is equal to 0, then this factor is eliminated and you end up with something linear, right? So we don't want that possibility of where you could be classifying the differential equation as linear and also Bernoulli, right? So what we do is we exclude that possibility to say n can't be equal to 0. Also, if n is equal to 1, so then you'd have p of x times y on this side, and then you'll have q of x times y on this side, but then you could easily combine it into a single term. In fact, if n is equal to 1, you end up with something that's separable, right? It might be linear and separable, right? So we want to remove that possibility as well, right? So we're going to define a Bernoulli equation to be one that's in this form, where on the left-hand side, it looks like the left-hand side of your linear differential equation, but then on the right-hand side, it has this additional factor here that makes it non-linear, right? If we rule out the possibility of n being equal to 0 and n being equal to 1. Right? So the fact that Bernoulli equations are so they seem, you know, like almost like a general case of a linear equation. It turns out that there is a special substitution that can be used that will convert a Bernoulli equation into a linear equation. So somehow there's some calculus and there's some algebra that we can do that will enable us to convert this differential equation into one that's linear. Well, why would we want to do that? Well, because we have a method for solving linear equations. Right now, we don't have a method for solving the Bernoulli. So what does this magical substitution look like? Well, so the substitution, and what it is, and I'll go ahead and use u like we've used u in all of our other substitutions. So the substitution u equals y to the 1 minus n, right, is used to transform or convert or change, whatever word you want to use, is used to transform a Bernoulli equation right, into a linear equation. And then after that, we know how to solve. So it's not necessarily the shortest of processes, but what I'm going to do is to show you in general. So I'm going to do the general transformation of this equation and turn it into something that's linear. But what will happen is we're going to end up converting it. Two things will happen. First, we're going to change the differential equation so that the dependent variable changes from y to u, right? That's the whole idea of the transformation. So basically, we're going to need to figure out how to convert dy dx into du dx, right? And again, like I said, the y will be converted into u. This equation will essentially take care of that. And then also, our resulting equation shouldn't have something where the dependent variable is raised to a power that's different from 1. So somehow after this transformation, this conversion process, we should get a differential equation where there is no dependent variable raised to some power that's neither 1 nor 0, right? So let's see what it looks like, right? So buckle up. All right, so let's write down. So we have, now remember, when we write equations like this, we often leave off something that's pretty important. Because it's easy to assume that implication is clear. But again, remember when you have a derivative like this is saying that y is dependent on x. So if y is dependent on x, then it means that u has to be dependent on x as well, because I'm taking y, which is dependent on x, and I'm raising it to this constant power, and I'm defining that as this other variable that I'm calling u. So really, this is like a key thing. So I'm going to go through, and everywhere I have a dependent variable, that dependent variable is going to depend on x, right? Right, so that's the equation that we have. So now, as far as, now, if I wanted to figure out what y is, some basic algebra will tell me that in order to isolate y, I need to raise both sides to a certain power. Well, what is that power? It would be a power that is the reciprocal of this, right? So right away, just using algebra, this will tell me that y of x is equal to u of x raised to the power 1 over 1 minus n. So 1 over 1 minus n, right? And that will, so basically this equation right here tells me how to convert the y into a u. So that's pretty straightforward. Not only that, but I can then take this and raise both sides to the power n, and that will give me a way of converting y to the n over. So this is true, and this is also true. Y of x to the nth power is going to be all of this to the nth power. So u of x all to the 1 over 1 minus n all to the nth power. But if I have a quantity that's raised to a power and then all of that is raised to another power, my property of exponents just says I can multiply these powers. So this comes down to be u of x to the power n over 1 minus n. All right? Okay, so I have this one highlighted. So that will become u to the n over 1 minus n. I have this taken care of. That's going to be u to the power 1 over 1 minus n. All that's left is now I have to figure out what dy dx is. And this is where we got to go back to wonderful calculus. In fact, the thing that is needed is implicit differentiation. So what I'm going to do is to take this equation and I'm going to differentiate it with respect to x. So we're going to differentiate this equation with respect to x, and this is what we will get. So on this side, I will get du dx, right? That's pretty straightforward. And then on this side, because again, y is a function of x, but it's raised to this power, what we're going to do, we're going to have to use our chain rule, right? So we're going to bring that power down. So we're going to have 1 minus n, that quantity, times, and then I have to subtract 1 from this. Well, if I have 1 minus n, and I subtract 1, then that's going to leave me with a negative n. So this is going to be y of x to the negative nth power. And then the chain rule says I have to multiply by the derivative of the inner function. And the derivative of y is going to be dy dx, right? So now this is the equation that we still have to do a little bit of manipulation, right? That will allow me to then replace dy dx. And then with these three things taken care of, I can then convert this equation into one that will be linear, right? So essentially, we're proving that this substitution will work, right? All right, so what do we have here? Well, this is fairly easy to solve for dy dx. And I'll do it in a couple stages. So let's say we have du dx. And now with the y of x to the negative nth power, I can use my reciprocal property. And I'll end up with 1 minus n over y of x to the nth power, and then times dy dx. And then if I want to isolate dy dx, what I can do is multiply both sides by y of x to the n and divide both sides by 1 minus n. So this implies that dy dx is equal to, let me write it like this, y of x to the nth power over 1 minus n times du dx, right? So there you go. In fact, let me go ahead and do this now. So I'm going to call this 3, I'm going to call this 1, I'm going to call this 2. So this is my new 1. This is my new 2. And then what I have for the derivative, this is my new 3. Right? And, well, almost. We'll see in a second that there's still a little bit to do here. In fact, let me undo that and do a little bit more. Because see, this is not good, or not quite what we want. It's not that it's bad, but it's not what we want, because we can't have 3 variables in an ordinary differential equation. I can't have a y and a u and an x, right? That's not going to work as far as an ordinary differential equation. But we know what y of x to the n is, right? We know what that is. Y of x to the n is what I already have labeled here as 2. So we don't have to do too much more work. It just looks really messy. So this is what we're going to do. So we're going to have the u of x to the n over 1 minus n all over 1 minus n times du dx. And this is my new 3. So this is going to be number 3, right? So with these 3 equations that we have, we're going to substitute it into our original Bernoulli equation, right? And do a bit of algebra. Like I said, I hope you're really strapped in, right? So let me restate the Bernoulli equation. So let's state that. So we have dy dx plus p of x times y is equal to q of x times y to the n. And again, the assumption here is that n is neither 0 nor 1. So now let's plug in these 3 things that I have highlighted. So for dy dx, we're going to replace it with this expression. So we're going to have u of x to the n over 1 minus n over 1 minus n times du dx, right? Plus p of x comes down, that's fine. That only involves our independent variable. That goes back to how we define our linear equations. And then y is u of x to the 1 over 1 minus n. And then that's equal to q of x times y to the nth, which is right here. So u of x times, or to the n over 1 minus n. All right, so what do we do now? Well, to simplify things, wherever there's a u of x, I'm just going to write it as u, right? So I'm going to go back to that sort of implied way of denoting a function that it's understood, again, especially because we have our derivative right here that tells us it's du dx. U is dependent on x, so I'm going to go through just a simplified, and I'm just going to get rid of these things. All right. So okay, let's do this. So I'm going to write this as 1 over 1 minus n, so that's my constant, and then I'm going to have u to the n over 1 minus n du dx plus p of x times u to the 1 over 1 minus n, and then is equal to q of x times u to the n over 1 minus n. Now remember, when we have a linear differential equation, right, the standard form for it to be linear is that we have to have a leading coefficient of 1. Right? So let's slowly go through and do some algebra to have a coefficient of 1 here. So the first thing I'm going to do is to multiply each of the terms by the constant 1 minus n. Right? So since I have the reciprocal of 1 minus n here, so let's write down what we're going to do here. So we're going to multiply the entire equation by the quantity 1 minus n, whatever that constant is, right? So that will eliminate this this term or factor. I'll still have the u, so I'll have the u to the n over 1 minus n du dx. But then this now has to be multiplied by 1 minus n, so I'll put that constant in front. But I still have my u there. I haven't done anything with the u's yet. And then this side has to be multiplied by the same constant 1 minus n. And then I'll have q of x and then u to the n over 1 minus n. And then remember, what we have to do is then divide each term, and there are 3 terms here, by this coefficient of u to the n over 1 minus n. So next up, we're going to divide by the factor u to the n over 1 minus n. So then that will leave us with du dx plus, now since this part here doesn't involve the u, I'm gonna bring those factors down, and then I'll have the u to the 1 over 1 minus n, and that's what I'm going to divide, because this is where I'm really going to see how things simplify. So I have u to the n over 1 minus n, right? And then equal, same thing here, bring down the 1 minus n and the q of x, and then I'll have the u to the n over 1 minus n, but look, it's divided by the same thing, the u to the n over 1 minus n. So it doesn't take, in fact, let me write that more clearly. There we go. So it doesn't take a lot of work to see that these two will be completely reduced, right? So that goes, that goes. So all that's left to do is to figure out what happens when I have u to this power, 1 over 1 minus n, divided by u to this power, n over 1 minus n. Well, think about it. You have your properties of exponents, right? If I have u raised to a certain power divided by u raised to another power, I have to subtract those powers if I want to simplify it, right? That's what the properties of exponent says. So it comes down to, what is 1 over 1 minus n minus n over 1 minus n. Let's do that off to the side, right? So let's do that off to the side. So if I have 1 over 1 minus n over 1 minus n, I already have a common denominator, right? So that's 1 over, or that's 1 minus n, and then this is just a 1, and then minus n. Well, looky there. That just reduces to 1. So what I have here is u to the first power, and that's what we need in a linear equation. So let's write it down and take a good look at it like this. So then again, this just simplifies to u to the first power, and then over here, in fact, yeah, I don't want to have the power there, but let me just take that off. But yeah, it's u to the first power, and then here we have 1 minus n, that quantity, times q. And this is now a linear equation. So this is linear, right? And so it's linear with dependent variable u and still independent variable x. And then from this, we can use our integrating factor method, right? Now, in principle, I guess you could memorize this formula, but when we go through a specific example, which we're going to do right now, I am not going to just jump from, what's given in the problem to this. I mean, you could do that if you're a formula kind of, person. That's not me. I'm a process person. I love the process, even it might take a little longer, but I think going through the process, it really highlights the key things that you need to focus on, right? That way, what if you misinterpret the formula? What if you're not sure where all these letters, because yeah, there are a lot of letters to keep track of, right? So this proves, I'm not going to state it as a theorem, but essentially we just proved the theorem that with the substitution of u to the u equals y to the 1 minus n, we can convert any Bernoulli equation into one that is linear. And then after this, we solve using integrating factors. So let's do an example of this. And for this example, we're just going to focus on finding the general solution. So here's our example. What is the general solution of, and here's our differential equation. So dy dx plus 6y, and then we have 3x times y to the 4/3, right? And it's that y to the 4/3 that messes things up, right? And it can be shown quite easily. Well, I mean, just by definition, this is not linear and it's also not separable. So it's an equation that, so this equation right here, it is neither separable, right, nor linear. Right? It's Bernoulli, right? So we can't use separation of variables. We can't use our integrating factor method at this stage, but what we can do is convert it into one that's linear. So let's go through and now that we have specific numbers to work with, hopefully you'll see how everything goes. So first we're going to let u be equal to y to the power 1 minus, well, what's my n? My n in this case is 4/3, right? So this is n. Let me just kind of highlight this. So that's our n. And then we have our 4/3 there. So then we simplify. Now that we can get an actual constant here. So this is y to the negative 1/3. Right? So that's our first equation. So u is y to the negative 1/3. Now I can solve this for y quite easily by taking each side and raising it to the power -3. Again, the reciprocal of this. So you have to be, pretty. In fact, let me write it. So y is equal to u to the -3. Right? And then let's go ahead and differentiate this. So if I differentiate this with respect to x, remember to use implicit differentiation where your chain rule is key. So dy dx is -3u to the -4th, but then I have to multiply by du dx. All right? So there we go. And then let's go ahead and just plug everything in, right? Let's plug everything in. So dy dx is going to be replaced with, so this implies -3u to the -4 times du dx. So that's this term, and then plus 6 times y, which is this term, u to the -3, is equal to, now this term, we have a 3x, and then we have y to the 4/3 power. Well, if I take y, which is this, so this is my u to the -3, and then I have to raise that to the 4/3 power, right? So let's go ahead and simplify a little bit. All right, so what do we have here? All right, so let's do a little bit of algebra and simplify this. So we'll have -3 over u to the 4th times du dx, and then plus 6 over u to the 3rd power, and then I have 3x. Now here, using another property of exponents, we'll have u to the -3, then I have to multiply the -3 and the 4/3, so that's going to give me u to the -4, which then I can write as 1 over u to the 4th. Right? So we're pretty close. So again, we can do this in stages just so that the algebra doesn't get too convoluted. Let's now divide each term by -3, so starting with the constant. So I'll have 1 over u to the 4th times du dx, and then dividing a positive 6 by that -3 makes it a -2 over u to the 3rd power. And then here we'll have our equal sign, and then this becomes a -x, right? And then I still have my 1 over u to the 4th. And then multiplying by u to the 4th, right? Multiplying by u to the 4th gives me du dx. U to the 4th times 2 over u to the 3rd power gives me a -2u. And then on this side, I have a negative x. And again, this is now my linear differential equation. So this one is linear. So now we switch our approach. We have to remember what to do for linear differential equations. And that's where we use our integrating factor. So in this case, this is the coefficient of my dependent variable. That's what we used to call p, right? This is kind of our modified p. So mu in this case is e to the integral of -2 with respect to x. Notice x is still our independent variable. That does not change with this substitution. And our integrating factor is e to the -2x. So take our e to the -2x and multiply the entire differential equation. So that gives me e to the -2x times du dx minus 2e to the -2x u. And then on this side, we'll have a negative x e to the -2x. And again, now for the linear equation, after multiplying through by our integrating factor, we want to look closely for that product rule form, right? So again, if I call this my f, then all of this is f prime, right? And then if I call this my g, then this will be, or this is my g prime. So I can see the product rule pattern there, and it still holds. So the left-hand side is the derivative of the product of the integrating factor, e to the -2x, times my unknown function, which in the linear equation is u. So u goes here, and then this doesn't change. So I have negative x e to the -2x. And again, using our properties of derivatives and antiderivatives, so if the derivative of what I have in the square brackets is negative x e to the -2x, so this implies that e to the -2x times u is the antiderivative of negative x e to the -2x dx. And then we look at this, and we have to use integration by parts. So I'm going to use my nice table method for integration by parts. So I'm going to use u in this. Now this u is not the u here, right? This is to allow us to do our anti-differentiation. So we have this. So I'm going to choose my u as negative x, and then that leaves the exponential function as my dv. So I can differentiate this polynomial repeatedly until I get a 0. And that's great for integration by parts, right? And then I have to integrate as many times. So I'll have 1/2 e to the -2x, and then 1/4 e to the -2x. And then remember, these coefficients, they alternate. I can pretty much ignore the bottom one, but I'll put the plus sign there. And then we use these products, u'd be, uv, and so forth, right? So that our nice little table tells us what our antiderivative is. So what do we have here? Let's give ourselves enough room. So e to the -2x times u, that's equal to, okay, let's write down the antiderivative now. Negative x times -1/2 e to the -2x. This gives me 1/2 x e to the -2x. And then minus, so that's a plus. That's also a plus. So now we have a plus 1/4. Where do we have there? So plus 1/4 e to the -2x, and then we have our plus c. So we have our plus c there. And now let's go ahead and let's see. So solving for u, we can divide each term by the, what do we have there? Yeah, so divide each term by e to the -2x. So I have a u there, and then I'll have 1/2 x plus 1/4 plus c over e to the negative 2x. But then I can rewrite this in this form. So u is 1/2 x plus 1/4 plus c e to the 2x. And this is great. This is our general solution, but this is the general solution for u. We want the general solution for y. How do we find that? Well, remember that in fact, let's go back up. Let's go back and look at all this wonderful work that we just did. And here we go. So y is u to the negative third power. So all I have to do is take what I found for u and raise it to the negative third power. So since y is equal to u to the negative third, so here now is our general solution. I'll write it, with the y of x emphasis. So y of x is all of this. So this 1/2 x plus 1/4 plus c e to the negative 2x raised to the negative third power. There we go. So this is our general solution. And that ends our Bernoulli process. So it really, again, if you're doing it from first principles, which is always my preference, because I get a good sense of the process, and I don't just get fixated on a formula and not really knowing, okay, why does it work this way? But there are two key steps. One is the conversion from the Bernoulli equation to the linear equation, and then two, solving the linear equation using the method of integrating factors, right? And this is considered, again, one of the standard substitutions that are used when solving and analyzing first order DEs. So again, we're going to go take a yoga break now, and then maybe I think in the next video, let's do another example of this, because it's such a fun exercise. So tune in then after your yoga break. See you then.